Okay, hello everyone. Can everyone hear me?
Yes.
Okay.
Yes, ma'am.
So, yeah, hello guys. Welcome to our event, Seeking the Origins, organized by SEDS-VIT. Today, we are joined by Dr. Stefanie Milam, who is a planetary scientist at NASA's Goddard Space Flight Center. She also serves as the JWST Deputy Project Scientist for Planetary Science. So today she will be discussing about the importance of the James Webb Space Telescope and its potential in exploring the cosmos. So without any further ado, I'll hand it over to you, Dr. Stefanie.
Thank you so much for having me, and thank you everyone for joining today. Hopefully I can give you a little bit of insight into what we're doing for the James Webb Space Telescope. Not only the science, but also just how things are going as far as commissioning and what the observatory is all about. So let's see if I can get this started for you. Everything look okay? Do you see a presentation?
Yes, we can see it.
Okay, great. So as was said, my name is Stefanie Milam. I'm the JWST Deputy Project Scientist for Planetary Science, which means I was brought onto this project to make sure that we could observe all things planets with the James Webb Space Telescope. I'll tell you a little bit why that's unique in just a moment. I wanted to point out a few things, though. The James Webb Space Telescope is not only a NASA project, it is also a joint partnership with the European Space Agency and the Canadian Space Agency. The science, though, is going to come from everyone from all over the world. If you are affiliated with any institution whatsoever, scientific or not, you can propose to use this telescope to do the science of your own dreams. And hopefully one day all of you will get to partake in conducting your own observations with the telescope. You can follow us along on social media. We have some fantastic social media teams that are working on the James Webb Space Telescope. The NASA one is pretty much at NASA Webb on any of your favorite platforms. And if you're interested in following me on Twitter, you can also do so as well. So I want to start with how the James Webb Space Telescope actually was conceived. So how it started was the Hubble Space Telescope had this project. The director decided that he wanted to look at a blank piece of sky and see what the Hubble Space Telescope could actually see. So he spent a lot of time just staring into this blank part of the sky. And what he saw is this video, actually as an image, which is now known as the Hubble Ultra Deep Field. This image is actually now been put into a video or a movie sort of a format so that you could see as we look at this image, we are actually looking back in time. So the galaxies that are closest to us, which there's over a thousand galaxies in this one tiny little image. But all the ones that are close to us are really pretty. They have these spiral looking shapes. Some of them are halos. But you'll see as we go further and further through the video, things start becoming more blobby, not so structured. And finally, they are a lot redder than the things that are at the beginning of the video. And this is all due to just basically how light is traveling towards us, but also it may be due to how galaxies actually form and evolve with time. And that's something that we really hope to study with the James Webb Space Telescope. So Hubble sort of reached, let's say, the teenage years of the universe. About a billion years or so after the Big Bang is as far back as it could go. So with the James Webb Space Telescope, we want to breach that boundary and go even further back in time and go to sort of the toddler years of the universe. So this would be after the Big Bang and after the cosmic microwave background, which has now been mapped, and the dark ages, where the first stars and galaxies actually started forming. So this is going to take us to the universe at its infancy, and hopefully we'll be able to learn things about how these galaxies have actually formed and evolved. So a little bit of the science that we're going to be going through, but I first wanted to briefly mention what a redshift is, or why we're looking at infrared light. And this is because...
Stefanie, sorry to interrupt. I think, for mine at least, the slides are frozen on the title slide.
Oh, okay.
Is anyone else seeing that?
Yes, yes.
We can only view the title slide.
Oh, okay. Let's see.
Sorry to interrupt.
Oh, no worries. Thanks for telling me. Let's see if I can do some tricks here. Sorry about that.
It was presenting. You were sharing your screen, but for some reason the slides were just showing the title slide and it wasn't going beyond that.
Okay. I'm going to try doing it this way. How does...
So, yeah, if you go to presentation, there. Yeah, no, that looks much better.
Okay.
Yep, you're on the title slide. Yep, perfect.
Okay, great. Okay, thank you, Peter. I appreciate you letting me know. Okay, so we'll start over. This is the Hubble Ultra Deep Field, as you can see it in this image. I'm going to play it so that you can see, as I was just saying, we actually made this image such that you can actually march back through time and look deeper and deeper into space. So if you'll notice, the galaxies that we're passing by early on in the video are, beautiful structured galaxies. They have, some of them are very spiral in structure, some of them are halo-like, but they're very well organized and quite spectacular. But as we get further and further into the video, we're actually getting further into the universe, towards the earlier universe. As I was saying, sort of the teenage years of the universe. And you'll see that these galaxies start losing their structure. They start becoming very blobby and globular-like. They no longer are spiral in nature. We don't know if this is actually a resolution problem or if this is just how galaxies actually form and evolve. And it's something that the James Webb Space Telescope is really going to help us get some insight into. And so we designed this telescope to actually look further back in space to discover the first stars and galaxies of the universe, just beyond the dark age and past the Big Bang. So this is going to be sort of the infant universe, and hopefully we'll get some really detailed insight into how galaxies actually formed and evolved with time. So I want to talk a little bit about what redshift is. So these galaxies, even though as we were looking at them in the early universe with the Hubble Space Telescope, they appeared to be red in color, they're actually emitting the same light that we see from our own sun and our own galaxy. But as light actually travels, because the universe is expanding, it's actually stretched to longer wavelengths. And so the longer it has to travel, or the further away it is, the more redshifted it becomes. And so this is why we have an infrared telescope, so that we can study something called the cosmological redshift. I don't know if I can hide this little thing. Oh, there, okay. So this is sort of a flip book of what I'm actually talking about. And these are images of some of the galaxies that were actually taken from that first video. And so the ones here on the left show you the more structured, spiral-like, fantastic looking galaxies. And then as we go further and back in time, or towards the right, we see things that aren't quite so structured and a little bit redder in color, actually. So by viewing the universe at different distances and different eras, we will get the evidence that we need to collect the details about how galaxies actually evolve, whether or not how they grow, what happens when they collide with each other or merge with each other. And we'll be able to study the most distant and earliest galaxies. And this is something that only something an extremely sensitive, large infrared space telescope can actually do. Another fun topic with respect to astrophysics is black holes. This is certainly not my area of expertise, but I always get asked about it, so I like to talk about it at least briefly. So Webb's going to look through obscuring dust to study the center of our own galaxy, which is Sagittarius A, and study the stars that actually orbit it. by taking high resolution spectrum or studying fingerprints of different molecules, we'll learn about the temperature, the speed, and composition of the material that's collapsing within black holes, not only in our own galaxy, but in others as well. And one of the fun questions that we hope Webb's going to actually address is what came first, the galaxy or the black hole? We're also going to be looking at how stars form and die. So what you're seeing on the right is a video of one of my favorite nebulas in our own galaxy. And this is the Eagle Nebula acquired with the Hubble Space Telescope. Or sorry, not the Eagle, it's called the Pillars of Creation, sorry. And so as the video plays, you'll actually see the optical light. The dust is actually obscuring a lot of the light that's emitted from stars that are embedded within this cloud. But then also it's hiding any stars or galaxies that's behind it. And so with infrared eyes, it's like having night vision goggles, and we can actually see through this cloud and into what's happening and see how stars are actually being born within these large structures across the universe. Clouds obscure things the same way in the universe, the way our own clouds in our atmosphere obscure things. You can't see the night sky, you know, stars, the moon, or whatever, if there's clouds in the sky. And so this is sort of the same concept, as these clouds are actually blocking the light that's being emitted behind them or within them. And so by going to longer wavelengths like the James Webb Space Telescope has, we'll actually be able to see through them. We're also going to be studying planets around other stars. And so to do this, we had to incorporate some interesting technology and capability with the James Webb Space Telescope. And one of which is called coronography. And this is where we basically take a disk and we block out most of the light that we are trying to detect with this super sensitive telescope. But by doing so, we can actually see fainter objects that are emitting heat and radiation at infrared wavelengths that are actually maybe around that brighter object. And so this is a technique that's employed routinely to detect planets around other stars. It's quite challenging. You have to have the right size aperture to block the starlight. And you have to have the sensitivity of a detector to actually find these fainter objects. So this is something the James Webb Space Telescope is going to have a fantastic capability to do. The other thing we'll be doing is we'll be actually looking for planets, or not even looking for, but we'll be studying planets that we know that are orbiting around their own star. Whenever we're in the right position with respect to that planet and star system, they'll actually pass in front of the star and obscure some of the starlight, just the same way the coronagraph did. And this is called transmission spectroscopy. So by doing this, you can study not only the size of the planet, you can study its orbit properties, and you can even study the composition of the atmospheres themselves. We see transits all the time. Venus tends to transit in front of the sun pretty routinely. This is an actual image acquired of Venus passing in front of our own sun. So this is something that's very familiar for us, even within our own solar system. Also think about things like an eclipse, for example. So this is something and a technique that we now use to study planets and other planetary systems. So as I said, whenever this planet passes in front of its star, we can actually start looking at the atmospheres. This is because an atmosphere has a lot of gas, and it has some amount of area that whenever it passes in front of the star, we can actually see through that atmosphere. And so when we look through that atmosphere, we're going to be looking for key signatures that maybe look a little bit like Earth's atmosphere, perhaps, or maybe some of the other planets within our own solar system. So we're looking for key ingredients for an Earth-like planet, things like water, carbon dioxide, methane, oxygen. These are all things that the James Webb Space Telescope is going to be very sensitive to. So even if we find an atmosphere that looks something like Earth, it doesn't necessarily mean it's going to be Earth 2.0, but it does mean that there's some very interesting chemistry happening and maybe some processes on that planet that are similar to our own, be it geologic, something like volcanoes or weather, or maybe it is something like biology. either way, it's going to be, intriguing enough that we'll actually follow up and study that planet a lot further in detail with other facilities, future space telescopes, or even ground-based telescopes. So just to highlight some of the science that we are already planning to do the first year of science observations, one of which is going to be studying the TRAPPIST-1 system. So this whole planetary system was actually discovered through this transit spectroscopy technique. And there's 9 planets. They're very peculiar because a lot of them actually reside in what we call the habitable zone. This is the region where you're far enough from a star that your water actually can exist as liquid water, but it doesn't freeze out and form ice. And so there's a number of planets within the system that are actually within that zone, which are very intriguing to study in detail with the James Webb Space Telescope. And these are some of our other planetary systems that we're also planning to study, including the Gliese 504b. So this is a planet here on the left. You can see it up in the top right there. It's either a big Jupiter-like planet or a brown dwarf in orbit around that star. One of the things we're really interested in is to understand what that object actually is. Other things include our nearest neighbor, the Alpha Centauri system, searching for planets within our nearest neighbor, but also studying the composition of those that are known, and as well as trying to find planets embedded within these planet-forming disk-like structures that we're now observing routinely at even longer wavelengths from the ground. And so this is something that we're really excited about and think that the James Webb Space Telescope is going to provide a whole new world of information for us. But the bread and butter for me is actually studying the solar system. The James Webb Space Telescope has this funny design and structure, basically to keep the telescope nice and cold so we can detect faint warm signals across the universe. But that also means that we can't actually point the telescope towards the sun. It is an infrared telescope, so it's very sensitive to heat and radiation that the sun and the earth and the moon actually all emit. So we can't point towards the sun, but that actually gives us a lot of access still within our own solar system since we're so close in, which is pretty much Mars on out. But this includes things like near-Earth asteroids and comets as they come into the inner solar system as well. This is a picture of the entire first year of science that we're expecting to do in the solar system with the James Webb Space Telescope. As I said, it includes everything sort of from Mars on out, including asteroids, near-Earth asteroids, as well as comets, satellites around Jupiter and Saturn, the rings of Saturn even, the ice giants and their satellites, and the tiny objects or not so tiny objects in the outer solar system. Mars is really a challenge for us, though. We have this extremely sensitive telescope that's designed to detect the first stars and galaxies of the universe. And now we want to point it at one of the brightest objects in the infrared sky, which is Mars. Mars is also the fastest moving planet that we can actually track with this telescope, and actually the one that we defined the speed limit for tracking capabilities for JWST in the first year of science. But we're going to be able to do really cool science, even though it is so bright. It is hard to actually observe at infrared wavelengths, but we will be able to map the full surface, the full disk of Mars. What you're seeing here on the right is an actual map that was acquired with a ground-based infrared telescope. But this took months, if not years, to actually acquire all the data because you're limited to only nighttime observations, whether or not there's clouds in the sky, and even winning time in a competed annual cycle on large telescopes. So with the James Webb Space Telescope, we'll be able to acquire these types of maps within hours of time, as long as Mars is within our observable field, which is a couple of months every few years. So we are planning to actually observe Mars in the first year of observations. And we do have capabilities in the near infrared where we can actually make these kinds of maps of things like water, methane, and other organics. And this is going to give us some key information, including upper limits on some of these organic molecules, and study things like ancient oceans that may or may not have existed on this planet. speaking of oceans, one of the hot topics in solar system science right now is ocean worlds. There's a number of objects that we believe have these subsurface oceans. And every once in a while, they have plumes of gas that actually escape from them. With the James Webb Space Telescope, we're actually going to be now studying what those plumes actually are made of. We have spectroscopy capabilities with the integral field unit, where each one of these little squares actually represents a full spectrum. So we can get maps across the full disk of something like Europa, for example, and we can map not only the plume and gas composition, but see if there's anything on the surface. So think about lava actually falling onto the surface of Earth. We'll be able to map those kinds of things to see what that activity is actually doing, and if new gas or molecules are actually freezing onto the surface actually after one of these outbursting plume events. So this is sort of a schematic of what I'm talking about with an artist's rendition of Enceladus, showing you some of these plumes actually escaping from a subsurface ocean. We still don't know what's causing them in any real detail, and it's something that's going to be studied very heavily in the future, including with future planetary missions. But another cool kind of volcano are things that we see like on the surface of Io. Io actually has hot volcanoes the same way we do. And not only do we see these hot volcanoes actually putting lava onto the surface of this moon, it's something that we hope we can actually image with the James Webb Space Telescope. We have another really cool instrument that acts almost like an interferometer, so it blocks a lot of the light out across the big mirror of the telescope so that we can see some of the finer, tiny little hot spots across the surface. And so this is a simulation that you see on the right, showing you with this instrument capability, we hope that we can actually resolve some of the lava volcano activity on the surface of Io. So this is another really cool project that will be done in the first year of observations. And then, of course, the discovery space of finding new moons or new rings around any of the planets in our solar system. Planets, minor planets, and even trans-Neptunian objects. These are things that are really interesting to study. Not only can we find them the way the Hubble Space Telescope has done, but we'll be able to characterize them. We'll know what kind of ice and dust actually are making up these rings. And that tells us a lot about the other satellites in that system as well. And then, of course, there's the whole realm of new discovery space. Interstellar objects are now a thing. And so of the two, one of them actually looked like a comet and one of them actually looked like an asteroid. We have no idea what these objects are going to look like as a bulk sort of classification of objects. Maybe there is a true dichotomy, or maybe there's even other variations. The James Webb Space Telescope definitely has the sensitivity and capability to study these objects in all kinds of detail that we haven't been able to do today. And then, of course, follow-up studies of other objects that we have studied before that have alluded to different things like different molecules being emitted or maybe surface properties. One such science case is the detection of polycyclic aromatic hydrocarbons within cometary coma. Some have suggested from early observations with the Spitzer Space Telescope that these very complex carbon molecules actually existed in the dust of a comet. And there is a project now with the James Webb Space Telescope to do observations of another comet that this has also been proposed in to confirm or maybe put an upper limit on whether or not these molecules actually exist. The bread and butter, though, for the sensitivity and the wavelength capability of the James Webb Space Telescope is actually the outer solar system. The Kuiper Belt and trans-Neptunian objects are very challenging to observe from ground-based telescopes. This is because they don't reflect a whole lot of light. They're pretty dark, and the sizes actually vary quite considerably. The James Webb Space Telescope will be able to characterize every known Kuiper Belt object that we know to date. So that's a significant capability that's beyond any other ground-based facility. And of course, our favorite Kuiper Belt object is Pluto. So this is an image from the New Horizons flyby mission. You can see this beautiful heart-shaped structure on the surface. now known as the heart of Pluto, but you also see a lot of variation across the surface, not only in colors, but also in textures. The James Webb Space Telescope is not going to have this beautiful resolution that the New Horizons flyby mission had, because we are actually in the inner solar system, but we will have a resolution that's sort of like what the Hubble Space Telescope has. So this is the image that the Hubble telescope took of Pluto right before the New Horizons mission. And again, you can see the variation in the colors across the surface. Maybe not the cratering and level of detail that you saw with New Horizons, but we did get actually to image the full disk of Pluto. So every single side, whereas New Horizons had a flyby and only got perspective of one side of the planet. So with the James Webb Space Telescope having a resolution comparable to what the Hubble Space Telescope has, we'll be able to map across the surface and study the composition of this planet. This is something New Horizons did in its flyby, but it had limited spectral capability. But you can see that the spectra actually does change from, say, for example, the pole of Pluto compared to where the heart of Pluto was. And so we'll be able to do this in much better detail. So that's some of the science that we're going to be doing, planetary science anyways, with a little bit of highlights of astrophysics with the James Webb Space Telescope, the first year of science. Now I'm going to talk to you about what this telescope actually looks like and why it's such a feat of engineering. Some of these images are absolutely fantastic. The most important thing I want you to grasp from them is not only the pure beauty of the observatory, but also how big it is. So in this image here on the left, you can see this man up on a lift, and his size and scale compared to the telescope is absolutely just, it's astonishing how big this space telescope actually is. So here's a cartoon and reference for that. Here's the Hubble Space Telescope. It has a primary mirror that's about 7 feet in diameter, with an average human being on the left. And then the James Webb's primary mirror is over 21 feet in diameter, whereas each one of these segments is over half of the radius of the Hubble Space Telescope. So it's absolutely huge mirror. It consists of 18 segments. Each of them are individually controlled, and they are made of beryllium with a gold polished finish. Just for reference, I'm actually below average of the average human being. So when I got to stand next to this telescope, I was almost the same size of one of these segments, and it was absolutely mind-blowing, the size and scale. But this also presented a lot of challenges for us, trying to test the telescope to make sure that it worked the way that we wanted it to, because it's going to be so far away from Earth that we won't be able to send astronauts there to maintain it or fix it if there's any problems that should occur. So one of the biggest challenges we had was figuring out how to focus this giant mirror remotely in space-like conditions. So extreme cold temperatures, as well as an under vacuum. We had to test all these mechanisms and ensure that they actually worked. This is a process that we call wavefront sensing and control. And it's basically making sure that each one of these 18 segments all work together and act like one single solid mirror. This is a really cool technology that's been developed, and we actually had some spin-offs of this that are applicable to everybody, everyday life. This is something that's now used for diagnosing eye conditions and accurate mapping of your eye. So the spin-off supports research in cataracts and keratoconus. And so you can actually imagine this working forward with LASIK procedures, for example, if you had eye apparitions. The main components of the telescope are the optical telescopes, the big gold mirror, the spacecraft, which is actually below the telescope, and the sun shield, which is this giant boat-like structure. But the true heart of the telescope is where all the science instruments live. We have 4 science instruments: a mid-infrared instrument, a near-infrared spectrometer, a near-infrared camera, and a fine guiding sensor that includes the near-infrared imager and slitless spectrograph. These were all provided by international partners So the mid-infrared instrument was from the European Space Agency with support by the Jet Propulsion Lab, NASA's Jet Propulsion Lab. The near-infrared spectrograph was also provided by the European Space Agency. The near-infrared camera was provided by the University of Arizona in the United States. And the fine guidance sensor with the near-infrared imager and slitless spectrograph was provided by the Canadian Space Agency. Now, we have an infrared telescope and we have to make sure it's actually really, really cold. This is because we want to be sensitive to these really, really tiny heat signals that are coming from the early universe. And so in order to do this, we developed this 5-layer sun shield that has an SPF of about 1 million. So you can imagine your favorite sunscreen has an SPF of about probably 30. Though you all are younger than I am and don't have the pasty complexion that I do, so you probably don't use any SPF, or if you do, probably a lot lower than I do. But anyway, so the way this works is basically the same way a sunshade actually works. Just by putting the telescope in the shade, we actually are able to cool it down significantly. So on the hot side of the telescope, which always faces the sun and the earth and the moon, it's actually about 85 degrees Celsius. This giant sun shield cools down the optical part of the telescope and the science instruments down to negative 233 degrees Celsius. So this is an extreme amount of temperature just by sitting in the shade. To shade something as big as this giant primary mirror that we have, though, meant we had to have a giant sunshade. And it's actually about the size of a regulation tennis court. So you can just imagine the size and structure and scale of this whole observatory. Now we have to fit this giant thing into a rocket. So how do you actually fold up a telescope so that it can fit into the fairing of a rocket to launch it into space? Well, this took a lot of challenge and innovation as well. And so our partners and some of our science teams and engineers actually worked to rig the telescope such that it folded together like origami, so that we could have a fully folded up telescope that would actually fit into the fairing of a rocket. This was also used for all the transportation that we did across the world, well, North America and South America, even before we even launched the telescope. This is what it looks like all folded up. I had the privilege and honor to actually go into the clean room just before we sent it down to French Guiana before launch. And as I said, standing next to something so big and beautiful, it was breathtaking, and I actually cried. I was so emotional and excited just to get to see the observatory before it left Earth. Well, now we have a folded up telescope. That meant we had to unfold the telescope once we launched it into space. So on our journey to our destination 1 million miles away from Earth, we actually unfolded the telescope in a series of sequence events. This included unfolding the mid-booms, then deploying the sun shield so that the observatory could start cooling down. Then we had to tension that sun shield so that it was thermodynamically proper. We then deployed the secondary mirror and then the wings of the primary mirror. All of this took about a month, and it was very terrifying. We didn't have the 7 minutes of terror the way the Mars lander did a year or so ago. We had almost a month of terror of actually making sure all these things unfolded. I will say, though, this was all under complete control. We have ground control from Baltimore, Maryland at the Space Telescope Science Institute. This is the same place that operates the Hubble Space Telescope and where the operations of the James Webb Space Telescope actually takes place. So every single one of these deployments, we were actually getting signals down to Earth telling us how the deployment went. And if something went wrong, we had controls and mechanisms in place that we could actually try to work through them and ensure that the deployment happened successfully. Fortunately, everything went beautifully, and we have a fully deployed telescope now. Transporting this thing, though, was quite a challenge. We had to do tests in Texas. We had to, well, first we did all the instrument assembly and test in Maryland at Goddard Space Flight Center, where I work. Then we had to ship the observatory down to Texas with its mirror and instruments to do the optical testing that I previously mentioned. And then we had to fly it to California at Northrop Grumman, where we installed the sun shield and the spacecraft. All of this meant we had some extreme challenges trying to transport this observatory. It only fit within a C5. And actually, there was only one of the C5s that the US government has that we could actually use for the observatory. So that posed quite a challenge. Not to mention challenging, we had to then ship the whole thing down to French Guiana for launch. And so this meant, you know, a journey by barge through the Panama Canal. It took about 20 days for the boat's journey to leave from Southern California to get there. But again, another fun and scary sort of adventure for the observatory. And of course, once we got to French Guiana, we had to install this beautiful sensitive telescope that we spent years testing. And then we stuck it on top of a rocket, which was the most terrifying thing ever for anybody that's been working on this project. And here you see the observatory actually on top of the rocket on the left, and then as it was installed into its fairing on the right. We had a beautiful launch on December 25th, Christmas Day, from French Guiana. Our launch was so beautiful and so successful and so nominal that it actually gave us a lot of assurance that we wouldn't have to use, as much fuel as we could have possibly used. We are a fuel limited lifetime mission. This means we have to use fuel to maintain the observatory. So the less fuel we use during launch and getting us on our journey, the more we had for operations of the observatory itself. And right now, with such a nominal launch and insertion to L2, means that we probably have a 20+ year mission. So we are currently at almost 60 days past launch now. All of our major deployments have successfully been completed as of January 8th, and we inserted into our destination at L2 on January 24th. And this was one of the last images that was actually taken of JWST with any sort of resolution, so as it was separating from its rocket. But there were other images that were taken. So a lot of people, ground-based amateurs and professional astronomers, have been following the James Webb Space Telescope on its journey. And this is just a quick video showing you the telescope actually traveling to its final destination. So where is that? It's the second Lagrange point. It's 1 million miles away from Earth. We are in orbit around the sun with the Earth. So we sort of, and we're in orbit around the second Lagrange point. So it's sort of this funny little orbit where we're circling a circle and following the Earth. But we're 1 million miles away. There's no access currently for any sort of serviceability to date. But who knows, now that we have a longer life mission, maybe either private industry or even NASA or one of our other space agencies will have developed that capability, and we can see about how that goes in the future. I encourage you to follow along on our journey. There's this fantastic webpage called Where's Webb. It tells you the current temperatures of the observatory, where we are in our commissioning phase, and it'll help you get some insight into what's going on as we lead up to science observations in the future. We released recently our first images. So we actually collected our first photons from the James Webb Space Telescope. This was fantastic. I was actually on shift working when these images came down. So what you're seeing are 18 stars, but they're all actually one single star. It's just that our mirrors after launch haven't been focused yet. And so you're seeing each one of our segments acting like an individual telescope. So you're seeing the same star 18 times. So we had to sort out which mirror was producing which one of these stars. And then what we'll do is we'll start stacking those images to make it look like one single image. And this is a process that's going to take a number of months to complete, but we're well on our way and have been working on this for the last few weeks now. We also took a selfie of the telescope. This is a fun image because it shows you, one, the actual mirror itself in space the fully deployed telescope, the secondary you can even see, and there's actually starlight being reflected off of one of the segments. This was a really cool perspective of the observatory, and one that I personally have got to have at NASA's Goddard Space Flight Center. So this is where we are with commissioning. It takes quite a while to make sure the telescope works the way we want it to. One, we have to focus and align the telescope, not only the mirrors themselves, but we have to make sure it's aligned to all of our science instruments as well. We then have to commission all of our instruments. We have to make sure they are calibrated, that their readouts are working the way we expect them to, and then we'll start producing our first data or images and spectra. So expect to see the first sort of things, pretty pictures coming from the James Webb Space Telescope sometime in the summer. And then once that happens, science actually begins. And we already have that first year of science already planned, as I said. So with that, I'm happy to take questions. I hope that you learned a little bit about the James Webb Space Telescope, and I hope that you're coming up with your own new science questions that you plan to address with this observatory. Thank you so much.
Thank you so much for taking such a wonderful session. So participants, if you guys have any questions, you can unmute and ask, or you can even put it in the chat box and we'll read it out.
Good evening, ma'am. I'm Nidhi, and thank you for the wonderful session, and it was really interesting. My question was like, will James Webb Telescope also help in the field of astrobiology?
Absolutely. So with respect to astrobiology, there's a lot of questions that I tried to allude to in this presentation. One is looking for other planets that are within their habitable zone and studying what their atmospheres may or may not look like. It's interesting to think that we might see another planet that has an atmosphere that resembles something like Earth, but we also have to remember the journey that Earth's atmosphere took in its lifetime. We went from everything from the heavy bombardment era, the moon collision, major impact events, dinosaur killing events, ice ages, hot ages, and even, impacts on life or from life itself. And so the glimpse of our Earth's life that has actually had life on it that we've known has been only an instant within its full journey. And so when we're looking at other planets, we have to remember we're looking at just an instant of its lifetime. So as I said, we're going to be looking for peculiarities within an atmosphere. It may or may not be from something like biology itself, but geologic processing or anything that's throwing the chemistry of a planetary atmosphere off is very intriguing and something we want to follow up with. And even in our own solar system, again, studying these subsurface oceans and understanding what that composition is might give us some insight into, other potentially habitable areas within our own solar system even.
Wow, that's wonderful.
Okay, so there's a question in the chat box. Why does the JWST have mirrors in the shape of hexagons rather than a big circle?
That's a great question. And there's lots of reasons, actually. One is it's easier to actually fold something and make it fit a lot closer together if it has straight, sharp lines. So by having hexagons, whenever we unfold or fold the telescope, it's a lot easier to have a seam, for example, that whenever you unfold it, it's easier to make those seams or segments fit closer together. If it was one solid piece of glass, it would not fit inside of a rocket, for one. And two, it would be a lot heavier. So by employing segmented technology, we're able to lightweight the telescope in ways that we wouldn't have been able to do if it was one solid piece.
Oh, good evening, ma'am. My name is Mihir, and I must say it was a really educative session so far. Just to add on to the previous question, I believe my question has something to do with the hexagonal mirrors. How is the scintillation of the JWST uniquely distinct from other telescopes, and how exactly has this come to be? Did the mirrors have a part in it?
I'm not sure if I understood your question. Will you repeat it for me?
Sure, ma'am. I wanted to know how the scintillation of the JWST, the fact that it has much less twinkling, irrespective of the atmosphere of the planet, compared to the other telescopes such as the Hubble telescope, the JWST is more precise, and what has led to cause this?
Okay, so that's a great question. Just by being above Earth's atmosphere, we don't see scintillation, which is a huge effect that we have for having a ground-based telescope in general. So what he's talking about is whenever the atmosphere is actually moving above anything on the ground, it actually makes stars or other objects twinkle, and it makes the starlight less refined. So we don't get it nearly as good of imaging as we could if we were above the atmosphere, for example, without other adaptive technologies, of course, which is something they're working on. So the James Webb Space Telescope, I wouldn't say has better imaging capabilities than the Hubble Space Telescope. It has probably comparable imaging capabilities. It is better at infrared light than the Hubble Space Telescope, but it's worse at optical light than the Hubble Space Telescope. So it sort of operates in the same precision and accuracy, just at a different wavelength. We can't access the infrared light that the James Webb Space Telescope has, or at least not the full spectrum, from the ground because of our Earth's atmosphere, actually. So if we're trying to study things in other planets that look like our own atmosphere, that's something that would be obscured by our own atmosphere. So we can't see light from things like ozone or carbon dioxide, because those are molecules that actually exist in our own atmosphere. And so it makes it actually opaque when we try to look out at those wavelengths from the ground. So if we want to study things that are in our own atmosphere, it's easy to do so not being below it.
Okay, so there's another question in the chat box asked by Abhijit. Why was Lagrange point 2 chosen?
That's a great question. So we decided to put this infrared telescope 1 million miles away from Earth, which posed a lot of challenges. One, it's a long ways to go. Two, we can't send astronauts there to maintain it, fix it, or upgrade it. And finally, it's such a large telescope that meant there was a lot of other challenges, including using enough fuel to get there, having a large enough rocket to get there, as well as other things. But there's an extreme advantage to sending an infrared telescope that far away. One, the Lagrange point is a gravitational saddle point. It's not an actual defined point, it's more like a well. And so by being in this particular location, we don't have to use as much energy to stay there. And we need to stay in some position that's relative to Earth so that, one, we can get our data down at a pretty decent rate, but also, so not only for communications, but also we want to have sunward access so that we can power our telescope. So we do have a solar panel on the bottom of the telescope. If we were somewhere a bit further away, we would have had to have extremely large solar panels, not to mention all kinds of other propulsion and momentum constraints if we were just in a free orbit, for example, or free floating. That in and of itself would give us fuel limitations that we don't have, or much more rigid fuel limitations than what we currently have. So being in a nice gravitational saddle point in a nice stable orbit gives us, like I said, a lot less stress on maintaining where the telescope actually is, but also for access to Earth and the sun. Additionally, by being that far away from Earth and the moon and the sun, we aren't impacted by radiation that's coming from these objects. So the Earth and the moon actually emit quite a bit of radiation, which would be noise for an infrared detector, because it's infrared heat that we would be sensing from those objects. So we're nice, cold, far enough away, but in a stable place that we don't have to use a lot of fuel. And yeah, that's why we're at L2.
Hello, ma'am. So this is Saran Loshan. Thank you for the wonderful presentation you gave. And my question is, I recently read an article about the James Webb Telescope that it is placing, like there's some kind of risk that is involved to make this telescope work. So can you brief it, like what are the risks involved in this Webb telescope to work?
I'm not sure I understood your question. Are you asking how we got the telescope to work?
No, what are the risks involved in, I read an article that says that there is a risk involved in making this telescope work. So
the risk involved in making the observatory work.
Yeah.
There were lots of risks, and every single day of commissioning, we're mitigating those risks, which has been fantastic. So our biggest risk was building such a large telescope that we actually had to deploy it. So having a deployable telescope was something that NASA or ESA or any other space agency hasn't really had. We've only had minor deployments, so things like solar panels popping out or a communication satellite. Those types of deployments are fairly routine and something that's very well rehearsed and practiced in space in general. So building a full-on telescope, especially for the amount of time and cost that's been associated with it, was very risky in and of itself. So that was probably our biggest risk. Now that we've fully deployed the entire telescope, though, I can tell you we no longer have that risk. And in the future, deployable telescopes are probably going to become far more common just because we've now mitigated that risk for other future telescopes. So that's something that's really nice to have and behind us now. It was very terrifying going forward. But the other risk was also the cost associated with it. Not only the cost as far as dollars go, but the cost of time. It took a considerable amount of time to build this telescope and to fully test it so that we were confident that it was going to deploy the way that we wanted it to, the way that we had practiced for it to do, and the way that we understood for it to do. So we did rigorous testing on all components of the observatory to make sure it was going to survive the launch environment, so the whole rocket shaking it. We wanted to make sure all the deployments worked properly. And so that meant, developing huge vacuum chambers that had cryogenic capability so that we could cool it down and test those mechanisms. The test as you fly philosophy is a heavy set one at NASA. We really want to make sure we understand the environment and how any space hardware is going to perform in a given environment. So if you're flying something to the sun, you want to know that you're going to survive the extreme radiation, the extreme heat. If you're flying to Mars, you want to be able to survive dust and the low gravity environment. There's all these types of things that we take into consideration, and that was something that was really challenging for the James Webb Space Telescope. So with the time that it took to do all of this rigorous testing, if something happened, we had to fix it. We had to understand why it happened. We had to either replace that component or whatever. It just meant that the technology was starting to fade a little bit with time as well, because it's been in development for 20 years, right? 20 plus years. So you can imagine the original instrument design may not be what it looks like today. And if we were to build a new infrared detector today, it probably wouldn't look what the James Webb Space Telescope is actually flying. And that's because the amount of time it takes to test and have assurance that things are going to work the way you want them to.
Ma'am, I have a question regarding the spectrum, especially why was particularly infrared chosen? Because there are you can go the other side of the electromagnetic spectrum, you can come back as well, but why was infrared particularly chosen for James Webb?
So the infrared wavelengths that were chosen were actually defined for this detecting the first stars and galaxies. So the redshift that we're anticipating the light from our first galaxies of the universe to come at us is actually in the near to mid-infrared wavelengths. And so that's why that particular wavelength regime was chosen. We pushed a little bit into the near infrared to have a slight amount of overlap with the Hubble Space Telescope. That was easy to do because the technology was already there. But then we also pushed into the mid-infrared because we wanted the overlap with the Spitzer Space Telescope, where we had a lot of other spectral capability that we don't have now with the James Webb Space Telescope. And so That gave us a nice broad spectrum that we could detect the first stars and galaxies across the universe, but also have access to key molecules that we can't do from the ground, including, as I've already said, molecules that are in our Earth's atmosphere that would block any of that radiation to study in other systems. So carbon dioxide and some of these other key ingredients like oxygen, ozone.
Thank you for the wonderful talk. So my question is, having multiple mirrors help in gaining like multiple perspectives of the same object?
So what's the question?
Having multiple mirrors help in getting like images from multiple perspective of our target.
So there's, so I guess you're referring to using a bunch of different types of telescopes to look at a certain object, or even getting different perspectives of an object itself.
No. My question is like, since we are having 18 mirrors, so will it help in gaining the multiple perspectives of our image we are getting?
Oh,
like,
okay. Okay, I understand your question. So we won't have 18 images of an object, and that's why we're working on focusing the telescope now. So we currently have 18 images because the mirrors, when we launched, we had to sort of stow them away in a safe position so that they didn't rattle and break during the launch environment. So they were in a nice nested and safe position. So once we got into a safe environment, we released them from that holding sort of resting place to where we could actually move them and focus them. So that first image that we took was just because the mirrors hadn't been focused at all. They were just kind of in this, okay, we launched the telescope and here's what they look like right now. So now what we're doing is we're basically tweaking each of these mirrors so that we can make all of those 18 dots or perspectives, as you say, act like one. So we're aligning them. Each one of the mirrors moves independently. So we're aligning them so that they act and perform like one single mirror. So we'll have one final image that's acquired from the James Webb Space Telescope.
Hi, I'm Rajdeep. That was a very informative session and quite an honor speaking with someone or hearing from someone who's been directly involved in the entire process. So my question is there any specific portion in space that the telescope will observe, like once the alignment process is complete?
Is there any, I'm sorry.
Specific portion of space, like a specific region in space that we will observe?
Okay, yeah. So because of the way the telescope's designed, it's the sun shield, and then it has the observatory sticking up like a sailboat, right? We can't move the mirror with respect to the sun shield. It's in a fixed position. So we're always pointing sort of, because the sun shield is always facing us, or the Earth and the sun, you can imagine we're always sort of looking at a donut on the sky. We can't see midnight with respect to the Earth. So if we were looking up in the sky at the same object that the James Webb Space Telescope could look at, we would have to almost look at the horizon. We couldn't look directly above us because it can't tilt that far away, because then the backside of the telescope would be exposed to the sun. So we do have a little bit of a sort of an angle on the sun shield. It is boat-like in some sense, so that we can roll it a little bit. So that's why it's like an annulus in the sky as opposed to just a hemisphere or a single strip. We do see a good chunk of the sky at any given time. And as we orbit around the sun with the Earth, that gives us access to the full sky at least twice a year. I hope that answered.
Yes, ma'am.
Thank you for the informative session. My question was just regarding the discovery of potentially habitable exoplanets with the telescope. So what factors or readings from the instruments on the telescope would like prompt further investigation of a potentially habitable exoplanet?
That's a good question. And I think as an astrobiologist, I would tell you we don't know. Because we only have one example of life, right? And that's here on Earth. So pretending that anything in the entire universe is going to be exactly as it is here on Earth, as we know it today, in the instant of that planet's existence is pretty far-fetched. Even in our own solar system, we see the variability across planetary atmospheres or environments, which is completely extreme. Orbiting Jupiter, we have an icy ocean world, so a crusty ice surface with oceans underneath it compared to a lava-emitting rocky body in orbit around Jupiter itself. So we know that there's extreme variability. I think to answer your question, though, what we will be looking at is not necessarily whether it's Earth-like, as I was saying. What's going to make us want to follow up on an interesting planet would be if the atmosphere has some sort of chemistry suggesting that something is happening. So in other words, it's not in an equilibrium-like environment. Something's provoking that chemistry to do something that we wouldn't see in a standard closed environment that's not being affected by anything. And so you can imagine something that would change that chemistry would be anything on the level of a volcano or a giant asteroid impacting and causing a huge dust storm or tsunami or impacting the atmosphere itself. There's also things like weather. Look at the storms that we see on things like Jupiter and Saturn. There's all kinds of weather patterns that can affect what we can observe remotely. So by not being there right next to it, taking images the way the New Horizons mission was able to do, or other planetary missions, we have to really use the spectroscopy and look for those molecular signatures that would suggest something is happening on that planet to make it different than what we would expect.
Thank you.
Mm-hmm.
Excuse me. So I'm Milind, and I have a question that can we expect to see life forms based on other elements, like other than carbon, in the solar system or maybe the worlds beyond?
I mean, life forms, if we wanted to see them with the James Webb Space Telescope, they would have to be the size of a planet. So we won't be able to see things directly in that sort of sense. As I was alluding to, we're looking for possibly an environment that may or may not be something that we think, even if it's not even like us, be something that's perturbed in a way that maybe life or some lifelike thing or even geology is actually affecting that planetary system. And with our own solar system, we don't have that beautiful resolution that the Hubble Space Telescope to get images of, or sorry, not the Hubble, of some of our planetary missions where we actually can see the surface of Mars, for example, and the craters and the mountains and the digging in the sand kind of a situation. What we're seeing is sort of a global picture of each of these objects in our solar system. And so again, it's more studying the chemistry of that environment and seeing whether or not something different is there.
Thank you for answering that.
Yes, ma'am. It's Rishabh. Thank you, ma'am, for such an amazing session. So there are basically several articles that I've gone through on the internet regarding JWST's observation of the early universe, looking back in time. So I had this one question: that does it matter which direction the JWSTs aim to obtain an image of the early universe?
That I can't actually answer. The one thing I can say, and just because it's not my area of expertise, I apologize. But what I can say is, if you want to look for something extremely faint and extremely far away, you want to stay away from the noisiest, densest part of our sky. So you want to stay out of the ecliptic of the solar system and look somewhere, away from where all of our asteroid belts and other planets and their satellites actually exist. And you also want to stay out of the plane of the galaxy. So looking somewhere that's sort of in a less dense part of the sky would be my #1 go-to if I was looking for the first stars and galaxies. But maybe that's a question for, I think you have Matt Greenhouse speaking to you tomorrow. He could probably answer more clearly.
Thank you, ma'am.
Hello, my name is Varshita, and thank you for this amazing session. My question is, how long is the James Webb Telescope going to observe and record information before, before it's decommissioned?
That is a fantastic question, and I'm so glad you asked. So when we launched and built this telescope, we were told by NASA and all of our authorities that we had to have a 5-year lifetime on this mission. So that meant once we launched the telescope and fully commissioned it, we had to provide 5 years of science capability. We were also told and demanded that we had to carry 10 years worth of fuel. And so we launched carrying what we predicted to be 10 years worth of fuel and promised science for 5 years. And as I was saying in my presentation, we launched so perfectly that we actually have done some calculations and believe that we're going to have well over a 10-year lifetime on this mission. That being said, when it comes to the end of the fuel, so when the gas gauge turns on and we start getting the blinking light that, your car's running out of gas, we have to actually stop operations and launch, well, not launch, but burn enough fuel so that we get away from the second Lagrange point, because other space telescopes are going to be there, other observatories and other things. And so we don't want it to be space junk in that particular location and cause, chaos. So we have to actually save our last bit of fuel to push it away and make sure it doesn't hit a planet or another satellite. But that's a great question. So I'm fingers crossed for 20 years. And we'll know a little bit more about that after commissioning's over.
Okay, thank you.
Great. So after the 5 years or 10 years, like until this 5 years and 10 years, is it going to keep orbiting the Lagrange point, or is it going to move anywhere else for further observation?
No, it'll stay there. It'll stay there.
Oh,
yeah.
Got it.
To move somewhere else, we would have to use a lot of fuel, and so that would just basically kill the mission. So it'll stay where it is.
Thank you. Thank you so much.
Yeah. Thank you so much, ma'am. I think we've kind of exceeded our session timing. So once again, thank you so much, ma'am, for taking time out of your busy schedule and conducting this amazing and informative session. I'm sure everybody here enjoyed it.
All right. Well, thank you so much for having me and all the fantastic questions. And again, follow us on social media. And thanks to Peter, my colleague that's been helping in the chat. If you have any questions, feel free to post them online or send them our way.
Right. Thank you, Sir Peter, for joining us as well. So yeah, to all the participants, particularly the freshers, you already know SEDS-VIT, we are currently recruiting. So do check out our Instagram, and we're finishing our round 1. The final date for attempting our round 1 is tomorrow. So be sure to go on our Instagram page and attempt our round 1 for SEDS-VIT recruitments. That's it. Thank you all for joining. And once again, thank you, ma'am and sir, for joining us.
And sorry, before the juniors can leave, we'll also have Mr. Matt Greenhouse tomorrow, who is the Science Instrument Payload Project Scientist of James Webb Space Telescope. Will be joining us again for an enthralling and a wonderful session. So all the participants, you guys can join the same link again tomorrow, same time. Thank you, ma'am. Thank you, Mr. Peter, for the wonderful session. Thank you very much.
Thank you.
Thank you, everyone.
Thank you.
Thank you.
Thank you.
Okay, yeah, participants, you guys can leave. The session's over. Once again, thank you for joining.
Thank you, ma'am.